Welcome to lecture series on advanced linear algebra. Today I will discuss about the decomposition of space. Since our objective is to find the simplified form of a linear operator defined over a finite dimensional vector space, to achieve our goal, decomposition of the space is useful. So, let me introduce the concept of decomposition of the space. Consider V be a finite dimensional vector space over the field capital F. Let W1, W2, Wk be the subspaces of capital B. W1, W2, Wk are said to be independent subspaces of V provided for 0 equal to alpha 1 plus alpha 2 plus alpha k, where alpha I belongs to Wi, I equal to 1 to k, implies alpha I equal to 0 for I equal to 1 to k. So, the subspaces W1, W2, Wk of the vector space V are said to be independent subspaces of V, provided if I have an expression alpha 1 plus alpha 2 plus alpha k equal to 0, where alpha I belongs to Wi, then certainly alpha I equal to 0. So, this implies for k equal to 2, W1 and W2 are independent subspaces of V, provided W1 intersection W2 equal to 0 subspace. But for k greater than 2 case, we have Wj intersection W1 plus W2 plus Wj minus 1. The sum of subspaces W1, W2, Wj minus 1 intersection the Wj equal to 0 subspace. So, it is simply not that W1 intersection W2 intersection Wk equal to a 0 subspace. It is, we are defining this independent subspaces of a vector space is basically saying that for any Wj, for this is basically for j greater than 2, basically greater than equal to, I can say. So, this is like this. So, Wj intersection W1 plus W2 plus Wj minus 1. So, this is basically sum of subspaces W1 and W2 Wj minus 1 intersection with Wj equal to 0 subspace please. So, this implies I can define small results like a lemma. Let V be a finite dimensional vector space over the field capital F, let okay. So, from the definition independent subspaces of the vector space B, I can write down this type of generalized results. Let it is like this: if V be a finite dimensional vector space over the field F, let W1, W2, Wk be subspaces of V, and W is equal to sum of subspaces say W1, Wk, then the following are equivalent. There are three statements which are equivalent type. First is if W1, W2, Wk are independent, then this statement is equivalent to saying that for each j 2 less than or equal to j less than or equal to k, we have Wj intersection W1 plus W2 plus Wj minus 1 is 0 subspace. And third one, if B1, B2, Bk are the basis, order basis for the W1, W2, Wk, then the collection of all these order bases, that is B equal to B1, B2, Bk, will be an order basis for this subspace W. So, let us prove this result please. This is very simple results which is coming as a consequence of the definition of the independent subspaces of the vector space please. First we will prove that A implies B, that is given W1, W2 and Wk are independent subspaces of vector space V is given to us. We have to show that this statement is equivalent to the statement, the second one, that B intersection of Wj with the sum of subspaces W1 to Wj minus 1 is a 0 subspace please. Let alpha j belongs to Wj and alpha j also belongs to sum of subspaces W1, W2 plus wj minus 1. Suppose like this thing. I have to prove that alpha j equal to 0 element. Alpha j belong to this ones and alpha j belong to this one, means alpha j belongs to the intersection of alpha j belongs to wj intersection w1 plus w2 plus wj minus 1. So, alpha j equal to something like alpha 1 plus alpha 2 plus alpha j minus 1. This is the definition of the sum of subspaces W1 to Wj minus 1 implies that any element of W1 plus W2 plus Wj minus 1 will be of the form of alpha 1 plus alpha 2 plus alpha j minus 1. So, alpha j equal to like this. So, this implies alpha 1 plus alpha 2 plus alpha j minus 1 and plus minus 1 into alpha j equal to 0, or I can write down alpha 1 plus alpha 2 plus alpha j minus 1 plus minus 1 into alpha j plus 0 plus up to 0 case equal to 0. See, up to alpha j is there, alpha j belongs to wj. So, there will be wj plus 1, wj plus 2 up to wk. So, wj plus 1 to wk I have taken 0 element only. So, that I can write down the same expression like this, but w1, w2, wk are independent subspaces, of vector space V. So, this implies alpha 1 equal to alpha 2 equal to alpha j equal to 0. So, this implies wj intersection w1 plus w2 plus wj minus 1 must be equal to 0 subspace. So, we see that A implies B. Now, let us see B implies A. B implies A means given wj intersection w1 plus w2 plus wj minus 1 equal to 0 subspace. It is given to us. I have to prove that to show if alpha 1 plus alpha 2 plus alpha k equal to 0, then alpha I equal to 0 for I equal to 1 to k. That is what I have to prove. Let j be the maximum value of I for which alpha I not equal to 0. So, the expression star can be written as alpha 1 plus alpha 2 plus alpha 3 plus alpha j equal to 0. So, this implies alpha j equal to minus 1 into alpha 1 plus minus 1 into alpha 2 plus minus 1 into alpha j minus 1. So, each of them belongs to your W1, W2, Wj minus 1. So, this implies alpha j belongs to Wj and alpha j belongs to W1 plus W2 plus Wj minus 1. So, B implies alpha j equal to 0. So, we see that alpha j equal to 0. Since alpha j equal to 0, then again from this expression I will have that alpha 1 plus alpha 2 plus alpha j minus 1 equal to 0, and use the same principles, repeat it and show that each alpha j equal to 0, I mean each alpha I equal to 0 for I equal to 1 to k. So, we will have alpha 1 plus alpha 2 plus alpha j minus 1 equal to 0. Now, using same logic we can show alpha j minus 1 equal to alpha j minus 2 equal to alpha 1 equal to 0. So, B implies A. Now, these two statements A and B are equivalent. Now, we want to show A implies C, A implies the statement C. Given B1, B2, Bk are the order basis of W1, W2, Wk respectively. Claim B consisting of B1, B2, Bk is an order basis for W. I mean to say they span the space W and they are also linearly independent. Certainly, B spans W, which is equal to W1 plus W2 plus Wk. So, now we want to show B is also a linearly independent set of B. Now, if I consider any linear combination of the elements of B1, B2, Bk, so it will give me any linear combination of elements of B1, B2, Bk will be of the form of beta 1 plus beta 2 plus beta k, where beta I is linear combination of basis elements Bi for the space Wi. So, this implies if beta 1 plus beta 2 plus beta k equal to 0 implies each beta I equal to 0 for I equal to 1 to k. From statement A, please. So, this implies, and beta is the basically linear combination of the basis element of Bi. So, this implies beta I, which is equal to something like say A I ai k and alpha I k type k equal to say 1 to d I, then this is equal to 0 implies that all a I k equal to 0. Since alpha I k, that is basically I can say no, this set, that is alpha I 1, alpha I 2, alpha I d 1, this is a basis element for the W I, and if I consider B I equal to say alpha I 1, alpha I 2 and alpha I d I, then I am saying that since beta I equal to linear combination of this set of elements, so definitely the coefficient has to be 0, all a I k equal to 0. So, this implies B equal to B 1, B 2 and B k will be a linearly independent subset of V and is a basis of W. Of course, this is a linear independent subset of W also. So, this one case. So, this implies A implies C also. So, based on the definition of the independent subspaces, let me introduce one terminology. This is called direct sum of subspaces. Let V be a finite dimensional vector space over the field say capital F. Let W 1, W 2, W k be the subspaces of V which are also independent. Then the sum of subspaces k given by W equal to W 1 plus W 2 plus W k is said to be direct sum of subspaces W 1, W 2 and W k. And mathematically, I mean we can write to give a special identity. So, I can write down W is equal to W 1 plus W 2 plus W k. So, W 1, W 2, W k which are the subspaces of the vector space V, which satisfied one of the conditions, I mean 3 equivalent statements what we have done just now, that A, B, C. So, that W 1, W 2, W k will be independent subspaces of V. Then the sum of subspaces of W 1, W 2, W k, if I write that is W, then W is said to be direct sum of subspaces W 1 to W 2, W k. For example, let V be a finite dimensional vector space over the field capital F, and let dimension of V is say n. Let Wi denote one dimensional subspaces of V. That is, if B equal to alpha 1, alpha 2, alpha n be an order basis, is an order basis, the basis of V, and Wi is equal to linear span of only alpha I, then V equal to can be written as direct sum of W1 plus W2 plus Wn. This is a very trivial examples I have taken. I mean, if V has dimension n, if I consider an order basis say alpha 1, alpha 2, alpha n, then subspace span of alpha 1 if I denote W1, subspace span of alpha 2 if I denote W2, and in general subspace span by alpha I only, that is Wi, then certainly V will be direct sum of W1, W2, Wn please, because this alpha 1, alpha 2, alpha n if I collect all together, this will be basis for the here subspace V, W equal to basically V itself. In our last example, I took subspace W, that is W1 plus W2 Wk, here W equal to I will say capital V itself. Let me take another example. Let V be the set of all n cross n matrix over the real number R. Then if we consider any matrix A belongs to V, I will be able to write A equal to A plus A transpose by 2 plus A minus A transpose by 2. And if I denote this is equal to A1 plus A2, then A1 is a symmetry matrix, is a symmetric matrix, whereas A2 is a skew symmetry matrix. See this one as a homework, that so that any matrix A can be written as sum of symmetry and skew symmetry matrix. So, this implies that if W1 denote the set of all symmetry matrix over R, and W2 denote the set of all skew symmetric matrix over R, then the set V can be written as direct sum of W1 plus W2. I mean, any element of V can be written as an element from W1 plus element from W2. That already we have seen that any matrix can be written as sum of symmetry matrix and Q symmetry matrix. Let me consider another nice examples. Let T be a linear operator defined on a finite dimensional vector space V over the field capital F. Let C1, C2, Ck denote the eigenvalues of T, and W1, W2, Wk denote the corresponding eigenspaces. Then W equal to W1 plus W2 plus Wk. I mean, the sum of subspaces of W1, W2, Wk of the vector space V will be basically direct sum of W1 and W2, Wk please, because we know the eigenspaces W1 and W2, if we take the intersection, that is a 0 subspace. In fact, here also Wj intersection W1 plus W2 plus Wj minus 1 will be equal to a 0 subspace. Already we have seen this one. So, based on that experience, I can say the subspace sum of subspaces W1 to Wk will be a direct sum of subspaces W1 to Wk please. Let me define a terminology called projection please. Let V be a vector space over the field say capital F. A projection of V is a linear operator on V. A projection say capital E of V is a linear operator on V such that E square equal to E, such that E square equal to E please. What is the meaning of this? So, let R and N denote the range space and null space of the projection operator capital E. We have E is basically operator from V to V. If alpha belongs to range of E, then alpha equal to some E beta, for some beta belongs to V. So, this implies E of alpha equal to E beta, that is equal to E square beta, which is equal to again E beta. This implies equal to again alpha. So, if alpha belongs to R implies that E alpha equal to alpha. Also, alpha equal to E alpha implies alpha belongs to range of E. So, E. We have for any alpha belongs to V, E alpha plus alpha minus E alpha. One can write like this. So, E alpha, this belongs to R, this belongs to R, and this belongs to the null space of E n, because E of alpha minus E alpha equal to E alpha minus E alpha equal to 0. So, we see that this implies any element of V can be written as a sum of element of the range space of E and element from the null space of E. So, this means that V can be written as direct sum of R plus N, where R is the range of the projection operator E and N is the null space of the operator projection operator E, please. Now, to understand more clearly, let me consider one examples. So, we see that this space can be written as a direct sum of range of E and null space of E, please. Okay, here I can also slightly modify it one things. The definition of my projection operator E I have defined like this, that a linear operator on V such that E square equal to E. Here R and N basically denote the range space and null space of the projection operator E I have defined. I will say that E is a projection operator on R along the null space your capital N, please. So, let me consider one examples. Find a projection operator E which projects this vector space V equal to R2 onto the subspace spanned by 1 and minus 1. That is, the range space is spanned by element 1 minus 1. Along the subspace spanned by 1 comma 2, the null space is subspace spanned by 1 comma 2. We have to define the projection operator capital E onto the subspace spanned by 1 minus 1 implies that R is equal to linear span of 1 minus 1. Along the subspace spanned by the 1 comma 2 implies that along the subspace spanned by 1 comma 2 implies that null space is equal to linear span of 1 comma 2. So, it is given E of 1 comma 2 equal to 0, it is given to us, and E of 1 comma minus 1 equal to 1 comma minus 1, it is given to us. Consider the standard order basis, B equal to E1 which is equal to 1 0 and E2 equal to 0 1. If I know the image of E1 and E2 under capital E, then we will be able to find the image of any element x comma y in R2. So, let us know what is the image of E1 and E2 under the operator capital E. So, to find that one, I have to express E1 equal to 1 comma 0 as a linear combination of the two elements 1 comma minus 1 and 1 comma 2 please, because this is two elements are linearly independent, we can quickly check it. So, this is equal to suppose C1 1 comma minus 1 plus C2 into 1 comma 2, we have seen that is equal to okay. We can quickly check if I consider E1 equal to 1 comma 0 which is equal to C1 times 1 comma minus 1 plus C2 times 1 comma minus 2, then C1 will be 2 by 3 and C2 will be 1 by 3. And similarly, E2 equal to 0 comma 1, then we will see that E2 equal to minus 1 by 3 into 1 comma minus 1 and plus 1 by 3 into 1 comma 2. I know the image of 1 comma minus 1 1 comma 2. So, this implies E of E1 will be equal to 2 by 3 E of 1 comma minus 1. E of 1 comma minus 1 which is equal to 2 by 3 into 1 comma minus 1, and other one is E of 1 comma 2 is basically 0. So, I am not writing this ones. Similarly, E of E2 will be equal to minus 1 by 3 1 comma minus 1. So, this implies for any element alpha equal to x comma y belongs to R2, x comma y equal to x into E1 plus y into E2. So, this implies capital E of x comma y will be x into capital E of E1 plus capital Y of E of E2. So, this is equal to x of 2 by 3 1 comma minus 1 plus y into minus 1 by 3 into 1 comma. So, we see that image of any element x comma y of the space R2 equal to x times 2 by 3 into 1 comma minus 1 and plus y into minus 1 by 3 into 1 comma minus 1. You can simplify this once. So, it will give you basically 2 by 3 x comma minus x minus 1 by 3 into y comma minus y, and if you simplify this will be equal to 2 by 3 x minus 1 by 3 y comma minus 2 by 3 x and minus plus you will have y by 3. Anyhow, so some this type of structure will get it please. Now, you can also solve some problems related to the projection operator which are given in the assignment sheet, and we shall utilize this concept of projection operator to simplify our operator please. So, we will continue in our next class.